Okay, good morning, everybody. So we're going to continue on with a little bit more of our lessons when it comes to combustion of an oil-fired piece of equipment. And this one here is we're going to be dealing with combustion air. Now, in the last couple of PowerPoints and videos that I've done, you could kind of get the idea of how we hammer home the importance of combustion in an oil heat unit, because without that we can't really achieve that practical clean running unit that we're trying to achieve. So air really is a major part in understanding and getting a oil-fired piece of equipment to run efficiently in a mechanical way. Okay, so really the effects of insufficient combustion air is kind of common in some of your units. When we look at a gas or oil appliance, we have to kind of look at the room that this piece of equipment is in. We have to think about where the air that's going to help support your combustion is really coming from. You know, so for proper operation of any sort of gas or oil heating appliance, you got to have sufficient outside air that has to be supplied to the structure to make up for the air lost from venting heating appliances, such as like your fireplaces, clothes dryers, exhaust fans, other areas of the building that are, you know, losing air. So for years, it's been assumed that when a heating appliance was in an unconfined space, and we talked about an unconfined space in a previous lesson, that there was sufficient air for both ventilation and combustion. That's really not the case anymore, especially with newer construction. You know, the older houses that we have, yeah, they were drafty. They were, you know, they were like loose construction, you know, so the windows were a little bit drafty, so you were getting air from other areas. So combustion air wasn't like so detrimental. I mean, the air was coming from somewhere. Today, no, that's not really the case. These houses are really being built to different standards. They're being built tighter, with more insulation, with more weather barriers, stuff like that, where, you know, you're reducing the amount of air changes per hour in a home. So now we have to start thinking about mechanical means to bring in the air that we need to help support the combustion of these types of appliances, so that we don't have smoke and soot and odors coming out of these things when they're burning. The combustion and makeup air requirements in the codes are based on half air changes per hour. So when you look at your NFPA 31, NFPA 54, your International Mechanical Code books and all that stuff, all of those codes that are dealing with the requirements for combustion air and ventilation and all that stuff, they base those codes off of a half air change per hour. Okay? Newer homes and conversions of electrically heated homes, the air changes could be reduced to literally a third or less air changes per hour. That's really a significant amount of air that's not really being moved or exchanged for fresh air. You know, I mean, if you ever think about it and you go into a home, like a newer home, and sometimes like how the home maybe might have like a musty smell, or the air just doesn't really smell fresh. Now, granted, maybe it could be because, you know, the home is just overall just filthy. But let's say for like a brand new home that's just built, all the windows are closed, and you go in and the air just doesn't smell clean. It smells like musty. Well, that's a sign that you don't have air exchange going on, air changes in the home. So fresh air really should be being brought in to the home through like some sort of like mechanical means. You know, air problems are most notable on the coldest day when heat loss is the greatest and there is a chance that the windows and doors are going to be closed for an extended period of time. That's usually when a lot of people notice, you know, that sort of like smell or problems with their air quality. When installing new equipment and troubleshooting problem equipment, the first determination that needs to be made is whether the equipment is actually in a confined or an unconfined space. In accordance with NFPA 31 and NFPA 54, an unconfined space is defined as any space whose volume is equal to or greater than 50 cubic feet per 1,000 BTUs or 20 BTUs per cubic foot. Okay, this is calculated on the sum of the total input ratings of all of your fuel burning appliances installed in that space. Okay, only areas connected to the space that have no doors or with fully louvered doors can be considered part of the unconfined space. Okay, if the actual free area of the louvers is not known, we can kind of use a little bit of like a rule of thumb. If they have wood louvers, we can assume to have about 20 to about 25% free opening area. If they're metal louvers or grills, we can assume to have about 60 to about 70% free opening. To add air to from an adjacent room into such a space, we can do it in a couple of different ways. Okay, the first way is we can have two openings between the room. Could be made 12 inches above the floor and 12 inches below the ceiling. The size of these openings are based on a 1 square inch per 1,000 BTU input of those appliances that are being used. If we want to add air directly from the outside of the structure, okay, we can make two openings, okay, again, and those sizes of these openings is again based on 1 square inch per 4,000 BTUs of input of all of your appliances. Now again, those two that we just read is right in your NFPA 54, NFPA 31s. Those are direct codes. Okay, alternately, if operating in a confined space, additional air may be added by a duct to the outside, sized on 1 square inch per 5,000 BTUs of input. So you have to go and you look at the input ratings of all of your appliances. And depending on how you want to bring in that fresh air into that space, you have to use those codes to help support the combustion air that we need to bring to that unit. If we don't have a proper amount of air, you're going to have a sooty, you're going to have a smoky fire, you're going to have a lot of problems. Okay, incomplete air-oil mixing. Improper mixing creates fuel in the combustion area and prevents complete burning. Remember the combustion triangle. You got to have air, fuel, and a heat source. In this case, we're using the electrodes, which is a spark. If any one of those three, particularly your fuel and air mixing, is not correct, you're going to have a crappy burn. Okay? Some of the causes that's going to happen that's going to make this occur is your mismatch of your fuel droplet spray and the burner air pattern. Okay? Inadequate air swirl or turbulence caused by outdated burner design. Okay, so you have an older burner attached to a newer piece of equipment that can create air turbulence and inadequate swirls and all that stuff, so your air and fuel mixture is not going to be correct. Improper adjustment of your air handling parts of the burner, so that would be like your primary and secondary air bands. They're just simply not adjusted to where they need to be. Off-center installation of the nozzle. Okay, your nozzle line may be cocked or bent for some reason, overheated. Defective or damaged burner parts such as the end cone, air tube, fan, or your motor coupling. Okay, cold oil produces larger fuel droplets. It increases the firing rate beyond those air settings. Flame impingement is another major problem that we can run into when it comes to how a piece of equipment is burning. The flame must not ever touch any solid surface of the burner, the end cone or the combustion chamber or heat exchanger. When that furnace fires off, the flame should be sitting in the center of the combustion chamber. The flame should not be touching anything. If you do have flame impingement, it's going to be caused by overfiring. The nozzle is just going to be too big. Excessive oil pump pressure, it's too much. Look at your your manufacturer specifications for that burner. If it's supposed to be at 100 psi, set it for 100 psi. If it's set for 150 psi, you set it for 150 psi. Whatever those specifications are, you got to do. Burners installed too high, too low, or off-center. Oh, well, okay, so it's just screwed up design to begin with. Whoever put it in went on, some website and did their own research and put it in, or you had some incompetent mechanic that came in and put it in, didn't know exactly what the hell they were doing, and they screwed up the design to begin with. Incorrect combustion chamber size or shape or base of the chamber is full of soot, or obviously if you have cold oil. Okay, that's a big problem if you have outdoor tanks, especially in the dead of winter because of those viscosity issues. The oil droplets are going to be bigger, and therefore it's not going to burn completely. The flame may be a little bit bigger. When it does light off, it's going to impinge on something. Okay, excess air, your CO2 and your O2. Okay, as we add excess combustion air to our furnace, the amount of nitrogen and unburned oxygen will also increase. The amount of water and carbon dioxide remain the same because we have already burned all of the fuel. Okay, the percentage of CO2 drops and the percentage of oxygen is going to start to increase. And by measuring either the percentage of CO2 or the percentage of unused oxygen, we can determine the quantity of our excess air on a unit. And as the percentage of O2 increases, your CO2 percent is going to actually decrease. So when we are setting up a burner, we can only do a couple of things to it. We can mess around with the air bands. We can mess around with our draft and stuff like that by making sure that it's clean. But we have to really honestly make sure that we're testing our units when they are firing. We have to do combustion efficiency tests to see where the efficiency level of these units are. Okay, right here, you say here's a beautiful chart on how we're talking about what happens when we add or lower our amount of air to a unit. So if we have, say for example, 50% excess air, our percent of CO2, we'll say it can be maybe about 10. We're measuring about 10. our CO2 percent is going to be about 11%. But as we add or remove the amount of air, that's going to affect our efficiency. It's going to affect how much CO2 we are releasing after the burn process. Okay, why do we control excess air? Well, we have to adjust it. We have to be able to make sure that we are creating good combustion. Okay, properly adjusting the burner air shutters is a compromise between too little air, which produces smoke, and too much air, which is going to lower the efficiency. Okay, so what we see here in this image, this is based off of 0% excess air. There's nothing else coming in to help this burn. So we know that we have to have a fuel and an air mixture. So, okay, so we have per 1 pound of air, or per 1 pound of oil, plus air, which we know is about 14.36 pounds, and air is made up of 20.9% oxygen and 79.1% nitrogen. When we take those two together, we're adding that stuff together. We're coming up with about 15.36 pounds of a product that we need to burn. After that burn, that changes, because now we have byproducts of combustion. Okay, byproducts of combustion is going to be water, it's going to be leftover nitrogen, it's going to be carbon dioxide. But look at our numbers. Look at what happens when we are, after that has occurred, the amount of water vapor is not considered in percents of your CO2 determination. It is just simply water. So we can create about 1.18 pounds of water after that combustion process with 0% excess air. We could present about 84.7% by volume of nitrogen. Okay, and we can create about 15.3% by volume of carbon dioxide. Okay, so it's relatively the same. Now here is at 50%. Okay, when we have that excess air, we can create a better burn. That's what we want to try to do. We want to be able to supply enough air to burn all of the oil that we are using to raise the efficiency of that furnace to its highest peak that we can possibly get. Okay, oil burners require a controlled amount of excess air above what is quote-unquote your theoretical value. Okay, and a big thing there, theory, to assure a complete combustion and a smoke-free operation. The excess combustion air serves as a safety margin to prevent incomplete combustion and smoke. Excess air, if you really think about that word, excess, it's leftover. It's additional. It's additional air that you are bringing in to help support the combustion process. If we deliver more than what we need, we can control how much is being delivered to our burner through our air shutters, our primary and our secondary air shutters. The air pressure in a building is always going to change no matter what. Okay, think about it every day. The temperature of the fuel is going to change. The draft is going to change based off of barometric pressures outside and the barometric pressures inside a home. See? So excess air gives us a safety factor that we need for all of those variations. That's why when an oil burner is firing, you don't see the oil mechanic come every single day back to the home and make adjustments on the air shutter to help, keep that unit running at a percentage of efficiency. It's because of the excess air. If I have enough air in the room or in the space that I'm delivering to that unit, the burner is going to do the rest. especially if it's set up correctly. When we increase air for more oxygen, excess nitrogen comes along for the ride. Okay, this dramatically is going to increase the amount of combustion gases that must be vented. Your heat exchangers need time to absorb the heat from the combustion gases. The more gas is forced into a heat exchanger, the faster they're going to travel through the heat exchanger. That is where our efficiency really is taking place, is how fast or how slow your combustion gases are making their way through the combustion chamber or heat exchanger. If it's going too fast, your furnace is losing the heat faster than it can be used. Okay? If it's going too fast, it gives the heat exchanger less time to pull that heat out and use it in the space. It's just going to go right out the chimney, and it's lost energy. Your efficiency is going to go down. We measure excess air by determining the percentage of oxygen, or our O2, in our combustion gases. For each 1% decrease in oxygen levels introduced into the combustion process, efficiency is going to increase by at least 1%. While some excess air is needed for complete combustion, we must set the air to the manufacturer's specifications to ensure maximum efficiency. OEM spec guides is a great tool to have if you're looking at what you're supposed to be setting your combustion air settings to. Okay, another problem with excess air is that it cools the flame. This creates incomplete combustion in that combustion area, and you're going to have carbon monoxide. Carbon monoxide levels are going to go up. The only way we can achieve a compromise between smoke and carbon monoxide and efficiency and all that stuff is by using a combustion efficiency test. You have to test what your units are doing. You have to. Whether you're doing a maintenance, whether you're doing a service call, you should be testing your combustion efficiency every single time you are working on a oil-fired piece of equipment. It's the only tool that we have to see what is going on in that process. To do that, we have to use a CO2 analyzer, or an orostat. Okay? Orostat is basically the name of the inventor that came up with this wonderful tool that we have. Okay? And it uses a chemical that absorbs CO2 from a mixture of gases without absorbing any other gas. Okay, the chemical that's inside there is a potassium hydroxide, because it has the capacity to absorb large amounts of CO2. Okay, when it does so, it's going to expand, and by measuring so much of it, it expands. We can now actually determine how much CO2 is actually in the gas. There are two main parts to this one test that we do. The first part is the pump, okay? And that pump is a sample tube that is inserted into the stack or replaced by a larger tube for over-the-fire sampling. And that type of tube, if you're really going to do a CO2 test over the fire using this, that tube literally needs to be about 30 inches long in order to really get a good reading of what your CO2 reading is over the fire, because the tube has to technically reach all the way into the center of the combustion chamber, because that's where all of your CO2 is going to be pretty much like at its highest. Okay, your sample is also going to have a yarn filter and water trap, which stops soot and water from entering the actual analyzer itself. You're going to have a sample bulb, or a rubber bulb, or a rubber flapper suction and discharge valve that allows flow in only one direction into the analyzer. You're going to have a rubber connector which seals the sample pump system to the analyzer. And then you have the analyzer itself. okay, which is a body which has two cavities or cups at the top and the bottom, connected by a narrow tube with an adjustable scale along the side. A valve system that either seals the gases and liquids inside the analyzer, or else lets a sample be pumped into the top cavity while the narrow tube in the lower cavity are actually sealed off. Then you actually have a diaphragm in there, or a flexible disc in the bottom cavity, which prevents a vacuum from forming inside the analyzer and lets the liquid in the bottom cavity to be drawn up into the narrow tube after the CO2 is actually being absorbed. So when we take this test, we stick our pump up on the top here and we depress our little valve down. And when we do that, we are going to now pump our little bulb, and we are going to draw CO2 into our analyzer. That CO2 is going to mix with our fluid. And when that happens, this fluid is now going to expand. It's going to rise up. And we can actually now measure how much CO2 is in that flue gas. Okay? One thing is really important is the CO2 test fluid is hazardous. Do not invert analyzers with the plunger valve depressed. And if that fluid does get on your hands, you have to wash it off immediately. It can create a little bit of like an acid burn on your hands. It can actually hurt. And that's it.